In this lecture, we're going to introduce exponential functions. Let's start with a definition. An exponential function f is a function of the form f of x equals a to the x, where a is greater than 0 and a is not equal to 1. What makes an exponential function different from, say, a polynomial function is that in an exponential function, the variable is the exponent. The base is some fixed number, and we require that that number be greater than 0. We don't want a to be 0 because 0 to the x power isn't that interesting. 0 to any non-zero base is 0, 0 to the 0 power is undefined, so the graph of 0 to the x would just be a horizontal line sitting on top of the x-axis with a hole at x equals 0. We don't want a to be negative because when you raise negative numbers to some fractional powers, you get non-real outputs. So there'd be infinitely many holes in the graph, and that'd be hard to work with. We also don't want a to be equal to 1, and it's pretty much for the same reason that we don't want a to be 0. 1 to the x power isn't that interesting. 1 to any power is just 1. That's even less interesting than the example where the base is 0, because that doesn't even have a hole in it. That's just equal to 1 the entire time. So the base is some positive number that's not equal to 1, and it's the exponent that varies. So as an example of an exponential function, we could use f of x equals 3 to the x power. The base is some fixed positive constant not equal to 1, and the exponent is the variable. When we evaluate this, we just plug numbers into the exponent. So f of 2 would be 3 to the second power, which is 9. F of negative 1 would be 3 to the negative 1 power. Remember that negative exponents are just reciprocals. So 3 to the negative 1 is 1/3. F of 0 would be 3 to the 0 power. Remember that any non-zero base to the 0 power is 1. And so in particular, 3 to the 0 is 1. So we're still just plugging numbers in for x, but what makes this a little bit different is that we're now plugging numbers into the exponent. Since we've already plugged some numbers into this function, let's talk quickly about what the graph would look like. If we wanted to sketch the graph of f of x equals 3 to the x, we could use some of these inputs that we just found. So for instance, f of 2 equals 9, that corresponds to the point 2 comma 9. Now that won't fit on my graph, but it would be way up here. F of negative 1 is equal to 1/3. So when we plug in negative 1, we get a point at 1/3. F of 0 was 1, so we'll plot a point at 0, 1. And what this is going to do is level off at the x-axis on the left side and shoot up very quickly on the right side. Let me give a quick explanation for why that would happen. As we plug in bigger and bigger positive numbers, we're raising 3 to bigger and bigger powers, and so those outputs are going to grow quickly. You may have heard of exponential growth before, that we usually use that phrase to indicate something that grows very quickly. That's exactly what this function is doing. As the inputs get larger and larger and larger, the function is growing faster and faster and faster. For the negative inputs, we're just taking the reciprocals of positive powers of 3. So it's making the denominator bigger and bigger and bigger, but it stays positive the entire time, and so the function kind of hugs the axis like this. There's a horizontal asymptote of y equals 0 on the left side. On the right side, there is no asymptote, it just shoots up forever. More generally, all exponential functions with a base bigger than 1 have that general shape. Let's talk about some of the properties. So the domain of an exponential function with a base bigger than 1 is all real numbers. You can plug any number you want in for x. You can raise a positive number to any power that you want. The range, however, is restricted. We always get positive output, so the range is from 0 to infinity, not including 0. When you raise a positive number to a real number power, you're always going to get a positive result. So the range is from 0 to infinity. As such, this graph has no x-intercepts. There is a y-intercept, though, and the y-intercept will always be the point 0, 1, because when you raise a non-zero base to the 0 power, you always get 1. Notice that the graph is continually moving up as we go to the right. That means that this function is increasing on its entire domain. It's increasing on the interval from negative infinity to infinity. And what's important about that is if a function is increasing the entire time, then we know it must be 1 to 1. And that seems like kind of a throwaway nerd comment to make about this function, but this is actually going to be important because what we're going to study are the inverses of these functions, And before we can talk about the inverse of a function, we have to know that it's 1 to 1. So that fact is a little more important than it might seem. We're also going to use that fact to help us solve exponential equations. We'll get to that later. So if you've got an exponential function with a base greater than 1, you've got an increasing function whose y-intercept is 0, 1. The domain is all real numbers. The range is restricted to just positive output. What if the base is between 0 and 1? Like an example of that would be f of x equals 1/2 to the x. You evaluate the function the same way when the base is between 0 and 1. You're just plugging the input in for the exponent. So f of 3 in this example would be 1/2 cubed. And remember that when you raise a fraction to a power, you just raise the numerator and the denominator to that power. 1 to the third power is 1, 2 to the third power is 8, and so f of 3 would be 1/8. F of 0 would be 1/2 to the 0 power, which is 1. Any non-zero base to the 0 power is 1. F of -2 is the reciprocal of the base squared. So the reciprocal of 1/2 is 2, and we raise that to the second power, and we get 4. Let's plot these points in the plane and see what this graph is going to look like. We said f of 3 was 1/8, so that point is just barely above the x-axis. F of 0 was 1. And f of -2 was 4. So the graph kind of bends down as you move to the right this time. Kind of missed this point. Let me just make that a little bit bigger, and then I'll make these bigger to mask that. This time the function will level off as you move to the right, because as you raise 1/2 to bigger and bigger powers, you're taking a half of a half of a half of a half of a half, and those fractions are getting smaller and smaller and smaller. Always positive, but getting smaller and smaller and smaller. So we've got a horizontal asymptote on the right side. On the left side, where we're plugging in negative numbers, we're taking the reciprocal of 1/2 and getting 2, and then raising that to larger and larger positive powers. And so on the left side, the graph is going to be moving up. In general, all exponential functions with a base between 0 and 1 have that same basic shape. Their domain is all real numbers. The range is restricted from 0 to infinity. Not including 0. You can't get 0 out of this function. The y-intercept is still 0, 1. But now the function is decreasing on its entire domain. As you move to the right, the graph moves down. A decreasing function will have y-coordinates that are continually getting smaller and smaller and smaller, though, and so this is still a 1-to-1 function. So let's recap. If the base is bigger than 1, then you've got a function that increases over its entire domain. And if the base is between 0 and 1, you've got a function that decreases on its entire domain. Let's look at the graph of a more complicated function here. Let's sketch the graph of f of x equals 3 to the x plus 2 minus 5. One way to graph this would be to plot a bunch of points, but we can actually use the transformations that we've learned before in order to graph this. We know what 3 to the x looks like. Think of that as our library function. This is what y equals 3 to the x looks like. We have a 2 added directly to the x. We know that that's going to shift the graph 2 units to the left. And then we have a minus 5 on the outside of the function. That's going to shift the graph 5 units down. So I'm going to use this point at 0, 1 as my reference point. I'm going to shift that 2 units to the left. So now I'm at -2, 1. Then I'm going to shift 5 units down. So 1, 2, 3, 4, 5. And I land at -2, -4. I need to keep the same basic shape, and perhaps to help me out, I'm going to translate this horizontal asymptote as well. The horizontal asymptote of the original graph was at y equals 0. We've now shifted that 5 units down, so now it's down here at y equals -5. Using that as a guide, I can sketch my graph. My graph isn't perfect. I didn't hit the correct y-intercept, but remember, we're just trying to get a sketch. We're not looking for perfection. This is a pretty good sketch of what y equals f of x looks like. Let's do another example of that. Let's sketch the graph of f of x equals 2 times 3 to the x. Well, again, 3 to the x is one of those increasing exponential functions. Goes through the point 0, 1. All exponential functions go through 0, 1 before you translate them in any way. And the 2 is a vertical stretch. We're going to stretch the graph vertically by a factor of 2. So all of the points are going to get twice as far away from the x-axis. In particular, this point at 0, 1 is going to get stretched to 0, 2. This point will get stretched twice as far away, and this point will get stretched twice as far away. These points will stretch further away, so they'll sit higher from the axis. And then we'll just draw the graph that goes through these. Let me start here. I don't miss anything. And then I'll stretch this out like that. And this is the graph of f of x. All of those transformations work the exact same way. With that in mind, I'd like you to try to sketch the graph of f of x equals the opposite of 1/2 to the x. Notice that the negative is on the outside. The base of the exponential expression has to be positive, so we can't have the negative on the inside. The negative's on the outside. See if you can come up with that graph. Okay, hopefully you remembered to change the shape of your original function. Because the base is between 0 and 1, this function is a decreasing function. It moves down as we go to the right. This is y equals 1/2 to the x power. We've multiplied on the outside by -1, which we know is a vertical reflection. That's a reflection over the x-axis. And so all of these points are going to flip below the axis. This point at 0, 1 will reflect a 0, -1. The graph's still going to approach the x-axis as we go to infinity, but now the function is an increasing function. As we move to the right, the graph moves up. It's just a vertical reflection over the x-axis of the original function. Now that we have a feel for what the graphs of these look like, let's do some algebra. Here we're given a graph, and we're asked to find the function that will fit it. Find an exponential function of the form f of x equals b times a to the x that has the given graph. We need to figure out what that vertical stretch is, and you might be able to guess that. And then we have to figure out what the base of the exponential function is. We can do this by translating what these points mean in terms of the function notation. The point 0, 9 means that when we plug 0 in for x, the output is 9. Or another way to say that is that f of 0 must be equal to 9. The function is b times a to the x power, and we're going to plug 0 in for x. We know that has to be equal to 9. A to the 0 power has to be 1, and so this is b times 1 equals 9, which means that b equals 9, and now we know that there's been a vertical stretch by a factor of 9. And again, you might have been able to guess that. Normally this starts at 0, 1. It's been stretched up 9 times as far away from the x-axis, and so the factor out front must have been a positive 9. So using this, we can now update our model. We know that f of x equals 9 times a to the x. But we still have to figure out what a is, and that's where the second point comes in. We know that f of 2 has to be equal to 1 because when x is 2, y is 1. Using our updated model and set that equal to 1. If 9a squared is equal to 1, then a squared is equal to 1/9, dividing both sides by 9. And now to solve for a, we take the square root of both sides. And normally when we take the square root of both sides, we have to put a plus or minus, but remember that a is required to be positive because it's the base of an exponential expression. So we don't even consider the negative solution. The square root of 1/9 is 1/3. And so we finally have our function. Our function is f of x equals 9 times 1/3 to the x power. We shouldn't be surprised that the base is between 0 and 1 because the exponential function was decreasing. Remember that the function decreases when the base is between 0 and 1. So the fact that we got a base between 0 and 1 is a good sign because it fits our graph. Let's try one more. Let's find an exponential function of the form f of x equals b times a to the x plus c with the given graph. We see we've got an exponential function that's moving up as we go to the right, which means that a is going to be bigger than 1. We know that we're going to get a base bigger than 1 because of the shape of the graph. The y-intercept is at 0, 4, and that might make you think that b is equal to 4, but be careful about that. We're going to have to check that out because there's also been a vertical shift. Notice that the horizontal asymptote isn't at y equals 0, it's been shifted up to y equals 1. Well, if the horizontal asymptote has been shifted up 1 unit, then that means that c must be equal to 1. Now we can update our model. We know that f of x is equal to b times a to the x plus 1. Now we can solve for b by using this y-intercept. We know that f of 0 is equal to 4, so that means that b times a to the 0 plus 1 is equal to 4. Well, a to the 0 is just 1, and b times 1 is 1, so that's b plus 1 equals 4, and so b equals 3. The graph got stretched by a factor of 3 and then shifted up 1 unit, and that's why the point wound up at 0, 4. We can once again update our model. We know that f of x equals 3 times a to the x plus 1. And now we need to solve for a. And how would we do that? Well, with the point that we've ignored so far. We know that the function has to go through the point 1, 6. So f of 1 is equal to 6 using our newest model. That means that 3 times a to the first power plus 1 is equal to 6. Subtracting 1 from both sides, we get 3 times a equals 5. Dividing both sides by 3, we get a equals 5/3. That would have been a difficult base to guess. But we get our final answer. This function is f of x equals 3 times 5/3 to the x plus 1. Notice that the base is bigger than 1, just like we predicted, because we've got an increasing function. That ends our introduction to exponential functions and their graphs. In the next section, we'll look at how we solve exponential equations by using some of these properties that we've talked about. Oh, and we're going to do some word problems too, so get yourself ready for that. If you have any questions about these graphs or any of the ideas in this lesson, let me know. You can see me in an office hour or you can send me some emails.